Hello everyone, I am Bishakh from IIT Kharagpur and I will be presenting our work on privacy preserving negotiation of common trust anchors across blockchain networks. So the background of this work is blockchain interoperability considering permission networks. So there has been an industry trend to create consortium networks as minimum viable ecosystem with minimal set of participants required to demonstrate short-term benefits. They often use different blockchain platforms such as Fabric, Corda, etc. So interoperability has been and is still an urgent requirement to achieve different goals, and by interoperability here we particularly mean verifiable data transfer. There has been several protocols proposed for verifiable data transfers and most of them use some proofs and attestations and some way to transfer data from one network to another network, which is termed as relay by this particular work in Middleware 2019. So the broad steps that are involved in this protocol are a query from the requesting network to the source network, which is validated against some access control policies, and then the data which is requested is attached with some proofs in the form of digital signatures or attestations. So this response along with this proof are sent back to the requesting network where the attestations are validated, and in order to perform this last step of validating attestations, these particular requesting networks need the public keys or certificates of the participants of the foreign network. As a result, we can see that identity configuration is a prerequisite of these verifiable data transfer protocols. So we proposed a cross-network identity configuration protocol in ICBC 2021 last year, where we split the system into two different layers, the data plane and the identity plane. And this identity plane took care of the exchange of this foreign network identity information. So we utilized two primary building blocks, SSI in the form of decentralized identifiers or DIDs and verifiable credentials or VCs. So the role of trust anchors in cross-network identity exchange is crucial. Here we consider two networks, network A and B, having organization A and B respectively. So these organizations use SSI, which are identities that are independent from the internal identities used by them in the blockchain networks. And these particular organizations use trust anchors in order to present some claims about themselves or to validate claims of other organizations. So here trust anchors 1 and 2 issue some verifiable credentials to organization B. Then organization B can present these credentials to organization A, and organization A can validate those claims that are in those credentials only if it also trusts the same trust anchors, which are trust anchors 1 and 2. So as a result, we can see that in this way, using the help of trust anchors, the identities and membership information can be validated and facilitate identity exchange. But instead of, apart from these two trust anchors, there can be many other trust anchors also, which might not be common in between them. So there might be trust anchors which is trusted by one organization but not the other one, and vice versa. So as we can see that we have certain questions like how do we determine the common trust anchors between the two different blockchain networks, and which trust anchors to use in case of validating different claims about the counterparty organizations. So we come to the problem statement, which is privacy preserving negotiation of common trust anchors. So organizations may not be comfortable in sharing its entire list of trust anchors, which actually reveals its affiliation with those particular trust anchors. So in case of an enterprise scenario, it might happen that revealing all trust anchors can lead to some loss of competitive advantage, or it might happen that these associations are actually with government agencies or political organizations or NGOs, which might be too sensitive for that organization to reveal to them, which do not associate themselves with those particular entities. So in order to define the problem statement, we can say that there is a holder which has verifiable credentials for certain trust anchors, and that set of uh, trust anchors is denoted as TH, and similarly the verifier trusts some trust anchors which is denoted as TV, and the goal is to reveal some subset of the intersection of TH and TV, which is basically the common set of trust anchors between the two parties, while not revealing any other trust anchors which are not common between them. So in the threat model, we consider the fact that trust anchors are in fact organizations which are well known and whose identities are known a priori and thus can be used to validate claims about other organizations. Hence, this universal set of trust anchors is actually well known to everyone. And we also consider the fact that parties can be malicious and parties can uh, tend not to follow the specified trust anchor negotiation protocol that we are proposing. So, although parties can themselves be malicious, we consider that the consortiums as a whole in which these parties participate are non-malicious. So, private set intersection is a very important concept, and this particular concept has been studied extensively, especially in the cryptographic community. So, PSI protocols allow two parties P1 and P2 holding sets X and Y respectively to identify the intersection X intersect Y without revealing any information about the elements which are not there in the intersection. But if we try to use PSI and there has been several protocols proposed for solving PSI, if we use those as black box, then also there we have a problem. So since the universal set of trust anchors T is known, it can be used by an attacker, and that attacker will basically input T as its own set of trust anchors, and by doing that we can see that it can easily get the entire list of trust anchors of the counterpart. So, in order to solve this problem of privacy preserving trust anchor negotiation, we propose two categories of solution. One involves active participation of trust anchors, and the other category is without any active participation of the trust anchors themselves. So, let us go through the first category in which the trust anchors are actively involved. Here we consider organization A from network A and organization B from network B. The first step of this protocol includes selecting a subset of trust anchors by each of these organizations. So we can see that org A selects T1, T3 and T4, and org B is selecting T4, T6 and T8. Now in the second step, these two organizations simultaneously send a request which contains the identity of the requesting organization, the identity of the organization with which it is negotiating the trust anchors, and delta, which denotes a particular time window, which we will use in the next step. So then a trust anchor responds to both these organizations only if it gets requests from both of them within this time period delta. So we can see that T4 here is responding to both of them with its own identity, and since it got the request from both of these parties. So if it happens that there is no common trust anchor selected, then these three steps are repeated till a maximum number of rounds or till a common trust anchor is found. So if a common trust anchor exists between these two parties, and if the max number of rounds is large enough, then eventually this protocol will be able to find out a common and reveal a common trust anchor between these two parties. But of course, this particular protocol has several limitations. So there are the issues include that trust anchors which are issuers or have information about the parties to which they have issued verifiable credentials. But for verifiers, there is no information with those trust anchors, and as a result, the validators need to inform the TS beforehand to make the protocol work. And obviously, there has to be some non-malicious and cooperating trust anchor to be available. So it might happen that trust anchors are malicious, or it might also happen that the trust anchors are simply not active. So there has to be at least one non-malicious and cooperating team. Also, the verifiable credential model promises that in the validation phase of VCs, verifiable credentials, the issuers, which are basically the anchors, don't need to be involved. But with the introduction of this protocol, we are forcing the issuers to be involved in the validation process, which is basically contradictory to the VC model. So we also propose a protocol without the active participation of the trust anchors. We already saw that a direct application of PSI as a black box is insufficient. Instead, what we need is we need to validate the inputs provided by the two parties before the actual intersection is computed, and this validation will involve validating the VCs issued to a particular holder by the trust anchor, Or in case of a verifier, a trust anchor is valid only if it is trusted collectively by the entire network in which that verifier is participating. So we propose a solution based on secure multi-party based computation to validate the inputs and then compute the intersection. So secure MPC is a cryptographic protocol that allows parties to jointly compute a function over inputs without revealing the inputs which are private. So this is the overview of the protocol, and here we see that the input of a party consists of the set of trust anchors denoted by their public keys, and this input has the signature on the claim of the party denoted by sigma, and the entire input is given as private input to the MPC protocol. And this MPC protocol involves validation of these inputs, which is basically validation of the signature, which denotes the verifiable credential, and this validation is done for both parties. And only if the validation of signature succeeds and the two public keys, basically the identity of the two trust anchors, match, then only that particular trust anchor's identity is revealed, otherwise it is not revealed. So MP Speeds library based implementation with Elgamal signature scheme shows promising results. We can see that this particular plot shows the size of the input sets, the two input sets varying from 2 to 120, and we can see that the time taken to compute the result is increasing linearly with the size of the inputs. But we can see in this plot that if one input set is kept constant at the size is kept constant at 20 and the size of the other input set is varied, then the time taken is actually fairly consistent, and this says that actually the time complexity of our protocol, or rather this Elgamal signature scheme implementation, depends on the size of this smaller input set. So thank you, and I will be happy to take questions, or please email them at my email ID.